Imagine you're trying to build something, maybe the next generation of aircraft or a high-performance car. You need it to be incredibly light, but at the same time, it has to be unbelievably strong, really durable. These industries, aerospace, automotive, defense, they're constantly pushing materials right to their absolute limits. So today we're doing a deep dive into exactly that, the real cutting edge of material science. We're going to unpack a really interesting recent research paper. It's all about optimizing these new generation materials. And our mission really is to give you a shortcut, a way to understand how scientists are taking a material many people know, AA7075 aluminum alloy, and turning it into something else entirely. They call them hybrid metal matrix composites. And these aren't just, incrementally stronger. They offer properties that traditional materials just can't match. Some surprising stuff in here with real-world implications. Okay, so let's set the scene a bit. Why this constant hunt for better materials? Well, it really boils down to a global demand, doesn't it? Across so many areas.
Oh, absolutely. You've got defense, aerospace, automotive, aviation, marine, even just general structural industries. Everyone wants lighter, stronger, tougher components. It's relentless.
And the starting point here, AA7075, it's not exactly a slouch to begin with, is it?
Not at all. It's a real workhorse material. AA7075 is an aluminum alloy, mostly with zinc added for strength. And it's picked for some really good reasons already. Excellent strength-to-weight ratio, that's key. Plus, it's pretty easy to form into shapes, resists corrosion reasonably well, conducts heat and electricity. Oh, and it's not pyrophoric, meaning it won't just burst into flames.
Okay.
So you find it everywhere. Aircraft structures, definitely. Car parts, marine applications. It's common stuff.
Right. So you have this already impressive material. How do scientists then take it, well, to the next level, make it even stronger? What's the basic idea?
The fundamental concept is reinforcement. You basically embed tiny, much harder particles into that metal base, the matrix.
Reinforce.
And in this study, they specifically looked at ceramic reinforcements. Ceramics are great for this because they boost, well, two main things. The tribological properties, that's fancy talk for friction, and wear resistance.
Ah, how it holds up to rubbing and scraping.
Exactly. And also the fundamental mechanical properties like its raw strength. Plus, ceramics tend to have really high creep resistance. They don't deform easily over time, especially under stress when things get hot. I mean, some of these ceramics, their boiling points are way up there, 1,000, even 3,000 degrees Celsius. They can take the heat.
Incredible. So what specific ceramic did they use in this paper?
They focus on two. First one, titanium diboride, TiB2. This stuff is known for being incredibly strong, chemically very stable, and really, really good at resisting wear.
How good are we talking?
Well, think about this. Its melting point is nearly 3,000 degrees Celsius.
Wow.
Yeah, and it's incredibly hard, around 1,800 HV on the Vickers scale. So perfect for things that see extreme wear, like ballistic armor plating or heavy-duty cutting tools.
Okay, TiB2. Got it. What was the second one?
The second one was zirconium dioxide, ZrO2. You might actually know it as zirconium.
From dental work, right? Crowns and things.
That's the one. But industrially, it's also prized for high hardness, good strength, fracture toughness, meaning it resists cracking, and again, great wear resistance. It can handle temperatures up to about 2,400 degrees C. In fact, people sometimes call it ceramic steel. Its stiffness, what we call the modulus of elasticity, is actually pretty similar to steel's.
Ceramic steel. I like that. So you take this strong aluminum, add super tough TiB2, add tough zirconia. But the key here is the hybrid part. What happens when you combine two different reinforcements? Is it just additive, or is there something more going on?
Yeah, that's where it gets really interesting. That's the whole point of hybrid metal matrix composites, or HMMCs. These are advanced materials where you deliberately put two or more different types of reinforcements, could be ceramic, metallic, whatever, into the metal matrix.
Okay.
And the goal isn't just addition, it's synergy. You're looking for synergistic improvements.
Like the whole being greater than the sum of its parts.
Exactly like that. The idea is that these HMMCs can show much better mechanical strength, better robustness, and significantly improved resistance to wear compared to using just one type of reinforcement, or, of course, compared to the original alloy on its own.
That sounds very promising.
Yeah.
So they figure out this combination, this recipe. But how do you actually make these things? How do you get these tiny ceramic particles mixed in evenly? That sounds tricky.
Yeah, the manufacturing is critical. The method they used here is called stir casting.
Stir casting. Like stirring soup.
Well, a bit more sophisticated than that, but the basic idea is similar. You introduce the reinforcements directly into the molten metal while stirring. The big advantage is that it's relatively economical and crucially scalable. So you could potentially do this on a large industrial scale, not just in a lab.
Right. That makes it practical.
So for this specific study, the matrix was our AA7075. They kept the TiB2 constant, always 5% by weight.
Okay.
Then they played around with the zirconia, the ZrO2. They tried compositions with 2%, 4%, and 6% ZrO2 by weight.
Varying just the zirconia.
Exactly. So they'd heat the AA7075 up to 800 degrees C in a furnace until it's fully molten. Then they add the pre-measured TiB2 and ZrO2 powders. And here's the key. Continuous stirring. They used a graphite rod and stirred it thoroughly 5 times every 10 minutes or so.
Why so much stirring?
To ensure homogeneity. You really want those particles spread out evenly, not clumped together. Clumping is bad for properties. They also added something called hexachloroethane. It's a degassing agent, helps remove trapped air bubbles from the melt, which could create weaknesses.
Okay. Like getting lumps out of batter.
Sort of.
Yeah.
And one last touch. Before pouring the molten composite into the iron mold, they coated the mold with the zirconia paste.
Why do that?
2 reasons. Stops the composite sticking to the mold, and it helps achieve a better surface finish on the final part.
Clever. So after all that careful cooking, they had their samples, and I assume they didn't just look at them, they tested them rigorously.
Oh, absolutely. They put the fabricated specimens through a whole battery of tests. Microstructural studies, using microscopes to see the internal structure. Hardness tests, tensile tests to measure strength and how much it stretches before breaking, and wear tests to check that friction resistance we talked about. And all of this was done following established ASTM standards, the industry benchmarks.
Okay, so let's get into the results. What did they actually see when they looked closely at that microscopic level? How well did the stirring work? Did the particles spread out nicely?
This is really where the why comes in. Why did some compositions perform better? Using scanning, electron microscopy, SEM, and also elemental mapping, which shows where different elements are, they found that for the sample with 5% TiB2 and 4% ZrO2, remember that one?
The middle zirconia concentration.
Right. For that one, the analysis showed a remarkably uniform dispersion of both TiB2 and ZrO2 particles within the aluminum matrix. The particles themselves were trainy, averaging around 110 nanometers, and they were spread out very evenly, often along the grain boundaries of the aluminum. This created a fine, well-ordered microstructure.
And that uniformity is good.
It's critical. It means the load is shared effectively across the material.
Okay, so what about the other compositions, the 2% and 6% zirconia?
Well, contrast that with the 6% ZrO2 sample. There, they saw a noticeable particle agglomeration clumping, and the distribution was much more heterogeneous, uneven.
Why would that happen? Too much powder?
Essentially, yes. At higher loadings, the tiny ceramic particles have more surface energy, and they tend to want to stick together rather than spread out nicely in the melt.
Okay, so clumping is bad. What about the 2%? Not enough reinforcement.
Pretty much. The 2% ZrO2 sample showed less clumping, which is good, but it ultimately resulted in lower mechanical properties compared to the 4%. It suggests that 2% just wasn't quite enough reinforcement to get the maximum benefit.
So 4% ZrO2 was the sweet spot.
Exactly. That uniform distribution they achieved with the 5% TiB2, 4% ZrO2 mix seems to be crucial for efficient load transfer and getting those property improvements. It's not just what you add, but how it arranges itself.
Right, the microstructure really dictates the performance. So let's talk performance then. How much stronger, harder, tougher did these materials actually get? What did the test show?
The results were pretty dramatic, especially for hardness. So the baseline AA7075 alloy, the starting material, has a Vickers hardness of about 55 HV.
Oh, 55.
All the hybrid composites showed significant improvement, but the star performer, again, the 5% TiB2, 4% ZrO2 composite, it achieved the highest hardness, 102.04 HV.
Whoa, that's nearly double.
It's an 85.45% increase compared to the base alloy. Really impressive.
That's huge. What about the others?
The 2% ZrO2 sample was also very good, hitting 98.98 HV. That's an 80% increase. The 6% ZrO2 sample, the one with the clumps, still improved, but less so, 92.24 HV, a 67% increase.
So the 4% was clearly the winner for hardness. Why such a big jump?
It comes down to how those hard ceramic particles resist deformation. They act like tiny obstacles within the metal. When you try to indent the material in the hardness test, the particles resist that localized pressure and help distribute the load more effectively into the surrounding matrix. It also relates to something called the Hall-Petch effect. Basically, these particles refine the grain structure of the aluminum, make the individual aluminum crystals smaller.
Okay.
Smaller grains mean more grain boundaries, and these boundaries act as barriers to dislocation movement. Dislocations are like tiny defects or slips in the crystal structure that allow metals to deform.
So more boundaries, harder for it to deform, higher hardness.
Precisely. The reinforcements plus the refined grain structure work together.
And the drop-off at 6% ZrO2, that's the clumping effect again.
Yes, exactly. That uneven distribution and particle agglomeration means the load isn't transferred as efficiently, and the bonding between the clumps and the matrix might not be as good. It compromises the reinforcing effect.
Makes sense. Okay, that's hardness. What about tensile strength? How much force could they take before stretching or breaking?
Right, so tensile tests measure that. We often look at yield strength, the point where the material starts to deform permanently. The original as-cast AA7075 alloy has a yield strength of roughly 107 megapascals, or MPa.
107 MPa.
Again, the 5% TiB2, 4% ZrO2 composite came out on top. Its yield strength was 123 MPa.
Okay, so that's about a 15% increase. Still significant, but not as dramatic as the hardness jump.
Correct. It's a solid improvement. The 2% ZrO2 composite reached 113 MPa, so a smaller increase. And interestingly, the 6% ZrO2 composite actually saw a slight decrease in yield strength compared to the 4%, down to 110 MPa.
Again, reinforcing that 4% sweet spot.
Absolutely. It really highlights that optimal threshold for reinforcement loading and dispersion.
And the reason for the strength increase in the 4%. Same reasons as hardness. Good dispersion, good bonding.
Primarily, yes. That uniform dispersion in creating a strong, stable interface or bond between the ceramic particles and the aluminum matrix is key for transferring the tensile load effectively.
Now, you mentioned earlier that sometimes when you make things stronger and harder, you lose something else. Ductility, the ability to stretch.
Yes, the classic trade-off. And that's exactly what they saw here. It's very common in these particulate reinforced composites. While the strength and hardness went up significantly, the ductility, measured by elongation, how much it stretches before fracturing, went down. For that optimal 4% ZrO2 composite, the elongation was reduced to about 11%.
Why does that happen?
Because those same hard ceramic particles that make it strong and resist deformation also get in the way of the dislocation movement that allows the metal to stretch and deform plastically. They pin the dislocations, making the material more brittle, essentially.
So, stronger, harder, but less stretchy. A design compromise engineers always have to consider.
Always. You gain some properties, you often sacrifice a bit of others. The goal is finding the best balance for the specific application.
Okay, so beyond just strength and hardness, what about wear and tear? That tribological performance you mentioned. How did these hybrids stand up to friction? That seems critical for moving parts.
Absolutely critical. And this is an area where aluminum matrix composites, AMCs in general, already tend to outperform basic aluminum alloys. But these hybrid composites took it another step further. The key finding, perhaps unsurprisingly by now, was that the AA7075 composite with 5% TiB2 and 4% ZrO2 showed the best wear resistance. It had the lowest wear rate under the test conditions.
Champion again.
It seems so. The mechanism here is quite neat. Those hard ceramic particles, the TiB2 and ZrO2, they don't just act as obstacles, they can also act as sort of solid lubricants during sliding contact.
Solid lubricants, how does that work?
Well, they help create a thin, lubricating film, sometimes called a tribal layer, between the sliding surfaces. This layer reduces direct metal-on-metal contact, which is what causes most material loss or wear. Plus, their inherent hardness means they resist being deformed or gouged out during those sliding interactions.
So they protect the surface.
Exactly. Now, the study did confirm, as you'd expect, that if you increase the load pressing the surfaces together or increase the sliding distance, the wear rate does go up. But even under higher loads, the composites still perform significantly better than the unreinforced AA7075 alloy.
And did looking at the worn surfaces afterwards give any more clues? You mentioned SEM analysis earlier.
Yes, they looked closely at the worn surfaces too. The SEM images showed grooves running parallel to the sliding direction.
Like tiny scratches.
Exactly. This indicates a wear mechanism called two-body abrasion. It's like tiny hard points on one surface are digging into and plowing through the other.
Okay.
But they also use that elemental analysis EDS on the worn surface, and they found oxygen.
Oxygen.
Hmm.
From the air.
Yes. The friction generates heat, and this heat can cause the exposed aluminum surface to react with oxygen in the environment, forming a thin, hard aluminum oxide layer.
And that oxide layer protects it.
It can act as a protective layer, sometimes called a self-lubricating oxide layer, further reducing wear. It's quite a complex interaction.
Interesting. Anything else from the elemental analysis?
One more thing. They detected traces of iron, Faye.
Iron. Where did that come from? The aluminum composite doesn't have iron.
Right, but the counter surface they were rubbing against in the wear test was a steel disc. Steel is mostly iron.
So some of the steel disc wore off onto the sample.
Exactly. It suggests the formation of what's called a mechanically mixed layer, or MML. Tiny bits of material from both surfaces get transferred and mixed together right at the interface due to the intense rubbing action. This MML can also influence the friction and wear behavior.
Fascinating. So many interacting factors at that tiny scale. Okay, let's try and wrap our heads around this. What's the big picture takeaway here? If someone asks us what this research found, what's the core message?
I think the central conclusion, the real insight, is that this specific combination, the AA7075 hybrid composite reinforced with 5 weight percent TiB2 and 4 weight percent ZrO2, really hit the sweet spot. It demonstrated the most favorable balance of properties, significantly enhanced mechanical strength, much higher hardness, and superior wear resistance compared to the base alloy and the other compositions.
And the key why behind that?
It really comes down to achieving that uniform dispersion and strong interfacial bonding of the reinforcements within the aluminum matrix at that specific 4% ZrO2 loading. It's all about getting the microstructure right. And it's worth adding, from a practical standpoint, TiB2 and ZrO2 are relatively accessible, cost-effective ceramic reinforcements compared to some other exotic options. That matters for real-world use.
Right, it needs to be makeable and affordable. So, zooming out, what does work like this mean for the future? For materials science, for engineering?
Well, I think it really underscores the huge potential of these hybrid composites. They offer a clear pathway to developing new generation materials that can genuinely meet the incredibly demanding requirements we see in aerospace, automotive, and beyond. Especially where you need that combination of high strength-to-weight ratio, excellent durability, and that high creep resistance, particularly for components that might operate at elevated temperatures. We're engineering materials atom by atom, almost.
It really is amazing how these tiny, precise changes at the nano level, getting that mix just right, lead to such dramatic improvements in how a material behaves in the real world. So here's maybe a final thought to chew on. If we're getting this good at controlling how these nanoscale particles arrange themselves, what other combinations could we try? Or what other tweaks to the manufacturing process, like stir casting, might unlock even more astonishing properties? Where does it go next?
That's exactly the right question to ask. It opens up so many possibilities. And beyond just strength and wear, how would this optimized 4% ZrO2 composite perform under other tough conditions? Think about long-term fatigue, maybe at high temperatures, or its resistance to different kinds of corrosion over years of service. Answering those questions could open up entirely new applications, maybe even in fields we haven't considered yet for these kinds of materials. The exploration is far from over.
Really fascinating stuff. Well, thank you for joining us on this deep dive into the world of high-performance materials. We hope this has given you, our listener, a valuable shortcut to understanding where material science is heading.